Okay, so this is a great problem to do, just to kind of practice the proof strategies, setting up the proofs and everything. So I thought it would be good for us to try this one. Okay, so let's do it. We have to prove this in two directions. Let's try the forward direction first. I don't think it really matters which one we start with. Let's assume that A is closed. Okay? Forward direction. I assume A is closed. I have to show that A contains all of its limit points. So what I should do is I should grab a limit point of A and show that A contains it. Okay? So let's do that. Let's let B be a limit point of A. And I'm going to claim that B is actually in A. A contains its limit points. So the first thing is, does everybody agree that I've set it up correctly? We're showing that A contains all of its limit points. So I'm just going to take a limit point of A. I'm going to try to show that B is in A. Okay, that's what we want to do. So B is a limit point. What's that mean again? By definition, it means that every open set containing B intersects non-trivially with A minus the set B. Seems like a mouthful. Okay. Well, I'm going to suggest we think about this by way of contradiction for a second. You know, if B was not inside of A, what would that mean? If B is not in there, then of course A take away B is just A, because B isn't even in there to begin with. So you're not really taking anything out of A that wasn't there to begin with. So it's just going to be A in that case. So let's just see what happens. Now, every open set containing B, right, so every time I have an open set U, if I intersect it with A, it's not empty. So somehow we have to use the fact that A is closed. How am I going to find an open set? If A is closed, then
Its complement is not.
The column going to be open.
the complement is
open.
open, right? The complement is open. That is an open set that we can work with. This is our assumption, guys, is that every open set containing B, let me just stop right there. Every open set containing B. Well, if I'm going to use that, I better find an open set that contains B that I can work with. It's like, starting off here, I don't have any open sets even mentioned. So I have to figure out how am I going to get one, right? And that's where the fact that A is closed comes in. Remember that a closed set, the complement of that closed set is open. Just by the definition of a closed set. So note that X minus A is open. X minus A is open. So let me draw a picture. Here's X. Here's A. And look at this, guys. B is over here, not in A. So look at that. X minus A, which I'm shading in right here, is an open set containing B, right? So then we can use this assumption. We have an open set that contains B. So also, B is an element of that, right? B is in the whole space, but it's not in A. So we know that that open set, which is X minus A, this is like my U, right? I'm using that as my U. When I intersect that with A take away B, but wait a minute, A take away B is just A. By assumption, that's not empty. This means that there exists an element that is both in A and not in A at the same time. Well, that's absurd. That's a contradiction. You can't have an element that lives in both the set and not in the set at the same time. This is just a contradiction. Okay, so this is a contradiction. Let me just make sure it's clear. This A right here is the same as A take away B. That's because the B isn't even in A to begin with. So I'm just using this little note right here, the assumption. Does that make sense? Let's look a little unsure of this. So let's just review the proof one more time. If we start with a closed set, we assume B is a limit point of A. We're going to show that B lives in A. Now the complement of that closed set is open. So we have an assumption that every open set that contains B. So, well,
that B is in that set.
I want B to be in A, but let's suppose it's not. If B is not in A, then B does live here in the complement of A. So here's an open set that contains B. Our assumption is that every open set that contains B creates a non-empty intersection right here. So then I'm just plugging things in. The U, I'm just putting in X minus A. And A take away B is just A because the B wasn't in A to begin with. It's like taking away nothing, right? So that intersection has to be not empty. But what you have here are two sets that could never have anything in common, right? So there you go. That's a contradiction.
Dr. Andy,
Yeah, what's going on?
there's another way of seeing it, like, so since you suppose that B is now in the complement,
Mm-hmm.
and since the complement is an open set,
Mm-hmm.
if you take any neighborhood around,
Stop right there.
oh, you're right.
Do we have any neighborhoods?
No, it's not a neighborhood.
Right, we're just in a general topological space. I knew that's where you're going to go with that.
Oh,
So I was
okay.
waiting to
Makes sense
jump on you. Yes, there were some people that on the homework, the problem 1, I think, in chapter 3, where you're supposed to show that the intersection of open sets is open, and they started talking about neighborhoods, and I basically had to put a big cross through the whole thing because, yeah, in chapter 3, we don't necessarily have neighborhoods. We can just talk about open sets. So. Okay, great. Let's go with the backwards direction. Let's assume, what am I doing? I'm assuming that A contains all of its limit points. And I would like to show that A is closed. I'm just going to do it this way. We need to, if I want to show, anytime you want to show that something's closed, you generally are just going to look at the complement and show that that is open. We need to show that X minus A is open. Okay. So let's see if we can do this. So in other words, it should be in my topology. So if I pick any point in this set, so if I, what do I want to call it here? If I just pick little x in capital X minus A, just grab a point that's in that complement there. Now that point is not a limit point of A because A contains all of it. Anything that's a limit point of A is in A. Here's a point that's not in A, so this X is not a limit point of A. It's not a limit point of A. So now we have the negation of the definition. A limit point is one where every open set containing the point has a non-empty intersection here. But if something is not a limit point, then there exists, right? So there exists some open set. I'm going to call it u sub x. This is an open set in this topological space with x inside of u sub x. So this is an open set. There exists an open set that does contain this point x, but which does not intersect with capital A minus that point, right? So, and u sub x intersected with A minus the set of x is actually empty now. This time it is actually empty. So there's an open set that contains x. This is for any x in the complement of capital A. For any x in the complement of capital A, this is going to be true. I'm just going to take this off of here, give myself a little bit more room. But this is empty. There's nothing in common there. Now x, again, x is not in A, right? If x is not in A, then what is A minus the set x going to be?
A.
Just A, exactly. So in other words, u sub x intersect A is empty. Okay. That is, another way of saying that is just that u sub x stays inside of x minus A. This is kind of what an open set is, right? An open set is one where every point inside the set, for every point inside the set, you can create a neighborhood. Now, I'm using that word. I shouldn't be using the word neighborhood in chapter 3. But of course, what I really am going to use, the alternative word for a neighborhood that does work in chapter 3 is the word open. So instead of saying there exists a neighborhood around this point, I'm going to claim that there exists an open set containing that point. And now that that open set is completely contained in this x minus A. Exactly. So guys, if you just take the union of all of those for every single x that is in x minus A. So do this for every single element outside of A. Create an open set containing it. Then this whole union, it's still open. Yep, this is open because it's an arbitrary union of open sets. An arbitrary union of open sets is still open. And where is it still contained in?
Us minus A, right?
Right. Every single one of these guys was contained in here. So if you take a bunch of union of all of those things, it's still contained in there, right? It's still contained in there. But x minus A, guys, x minus A is also contained in this union, because basically x minus A, let me just write that down first, is contained in the u sub x's. Why is that? Well, you grab any point here, grab any point in here, like we did in the proof. There will be a set u sub x that that point belongs to, and therefore belongs to the whole union. So what I have, guys, is subsets both ways. I have subsets both ways, so I'm going to conclude that x minus A is equal to this union. It's equal to that union, and that just means then that it's open, because this side is open. So then this side has to be open because it's equal to it. What do you think? Does that make sense? you know, we're used to checking that something is open by trying to draw neighborhoods around the point, and I know we haven't had a lot of practice yet getting away from neighborhoods. In chapter 3, that's what we're doing. We're getting away from neighborhoods, and we're just talking about open sets. So the trick to this problem is that when you grab this point that is in x minus a, instead of drawing a neighborhood around it, you'd like to just draw an open set around it. That's the difference between chapter 2 and chapter 3. You want to draw an open set around this point. What allows you to do that? It's the fact that x is not a limit point. If it's not a limit point, then there does exist an open set containing that point with some other property that we then wrote down. Okay, and that's how you create that open set that you want. This use of x is like the neighborhood that we would have had in chapter 2. This is playing that role. And that open set has x in it, and then this condition is what allows you to then show that that open set is contained in the complement of the set. So this is a little trickier than the previous example, but you know, I think it's still kind of a nice problem. Okay, so far so good. All right, let's do some more. I've got a bunch of problems. I'm about halfway through my sheet. I think we're about halfway through our time. So far, so good. Okay. Let's do some more stuff on chapter 3. Okay. I'm going to challenge you guys real quick. I'm going to challenge you guys with something. I think you're going to solve this challenge. Okay? Everybody needs to think real carefully with me here. Suppose that f goes from x tau, so that's a topological space, and it goes to y, and suppose that this is a function. Now at the moment, y is just a set. I don't have a topology yet on y. I have a topology here on the input space, but y is just a set. Now what I'm going to do is I'm going to define what it means for u to be open in y. In other words, what I'm going to try to do is make a topology on capital Y. I don't have one yet. I don't have a topology on capital Y yet, but I'm going to try to make one. It means I have to tell you what the open sets of Y are going to be. Okay, so I'm about to fill it in here, or you guys, I should say, are going to help me figure out what should I say here. The question is, what do you think I should say here? What would be the natural condition if something is going to be open in Y? Now we already know what the open sets look like here, because we have tau already. What do you think would be the natural thing to put over here?
The reimage.
Pre-image?
Yes.
Of
U.
Of U
is open
is
It's
open.
and x.
That's it.
Hmm.
See, I knew you were going to I knew you guys were going to accomplish my challenge. Exactly. This looks familiar, doesn't it? From chapter 2, this proposition that I'm going to ask you at your graduation. The pre-image of an open set is still open, right? So if this is going to make any sense at all, now wait a minute. That was for a function to be continuous. In chapter 2, the pre-image of an open set should be open. So if I create a topology on Y with this definition, I bet you that the function f will be continuous. Okay, in fact, that's one of the things we're going to prove here. So I have like 3 parts to this problem. The first thing I want to do is prove that this gives me a topology on Y, that this definition gives me a topology on Y. So prove that. There's nothing bizarre about this. Like everything all of this problem is just totally natural. If we just take the set of subsets of Y such that U is open, okay, as we defined it right there, that this forms a topology. Of course, I'm going to call this tau prime on Y. So we have to remember what a topology is. There's a definition for that. Let's just do that part first. Let me erase the rest over here. My camera still doing okay?
Yeah.
Okay, super. Okay, so let's take a look at showing that this is a topology. Can you guys remind me what's the first part of the definition of a topology? So there's two specific sets that always have to be in the topology. Remember?
X and the empty set.
Exactly. So the empty set, and actually in this case, is going to be Y. So we have the whole space as well as the empty set itself has to be open. So let's just figure out if that's the truth. So if that's true using our definition. So is the empty set in tau prime?
Yes.
Let's look at the definition. So this is tau prime here. Is the empty set open using this definition? Well, if you take the pre-image of the empty set, what do you get? I'm putting in the empty set right here.
Empty
Yeah,
set.
nothing can map to the empty set. So this is just empty, and that is open in X. Because remember, we already have a topology on X that we're assuming. So the empty set is open in X, it's in the topology tau. Okay? How about the whole capital Y? Is that in the topology? Well, to figure that out, I have to see whether capital Y is open. So I take the pre-image of it. If I want to know if something is open in Y, I just take the pre-image of it and figure out if it's open in X, at least if you believe my definition. This is just a definition, right? I can make up whatever I want. This is the definition I made up. So what is the pre-image of the whole capital Y going to be?
It's X and
The whole
it's
X.
that's in tau.
Because everything in X, remember, f of every single thing in X is going to end up in Y. Okay? And so this, of course, is also open in X. It makes sense, right? That to show that the empty set and Y are open, we're going to use the fact that the empty set and X are open. Okay, so this is, I believe, what in the
Part tau.
notes is like the lowercase I. Now let's go on to the next one. What does the second requirement on a topology say?
The intersection of two
Intersection of two
elements in A.
open
tau,
sets, right,
and
has
they're
to still
open.
be open. Exactly. So let's suppose that U and V are in tau prime. And I need to prove that U intersect with V is still in tau prime. Okay? So this just means, again, this just means that these two sets have this property here, right? So the pre-image of U and the pre-image of V, those two pre-images, those are open in X, just means they are elements of tau. Right? What would you like me to do next?
So the intersection belong to tau.
Right, so since tau is already a topology, we're assuming that tau is already a topology on X, right? Then the intersection
Is in tau.
is still in tau. Exactly, right? Okay, now what do I need to do?
So you're gonna
I have to show, let's figure out what are we trying to prove here. I'm trying to prove that U intersect with V is in tau prime.
So we can say that the pre-image of U intersect pre-image of V is equal to U intersect V.
This is what you want to look at, right? You want to ask yourself, is this in tau? Well, but this is one of the things, I think you guys proved this on one of your early homework assignments, that the pre-image respects intersections. So this is just the pre-image of U intersected with the pre-image of V. Isn't that great? So you just use that, and so then that is an element of tau. That is an element of tau, and that means that, I'm running out of room here, but I think I can squeeze it in, U intersected with V is then, by definition, in tau prime. All right, it's not bad. So tau prime is closed under intersections. And that's how you prove it. Okay, let's go, what's the third thing we have to have here?
Arbitrarily many? The union of any atoms.
Not finite here. So the finite is for the intersections. For the unions is arbitrary. So if we take an arbitrary family of open sets in tau prime and take the union, it should still be in tau prime. So let's do that. Let's let the set U sub I be a family of sets in tau prime. So you're just taking an arbitrary family of sets. Yeah, so make sure you keep the intersection and union things, they're not quite the same, right? Intersections have to be closed under finite number of intersections, but unions has to be for arbitrary families of sets. So let's say we take that. So then by definition, the pre-image of U sub I, right? If you take the set of all of those pre-images, what do you know about them? Where do they live?
They live in us.
They live in X, but more specifically,
Tau.
in tau, exactly. These belong to tau because that's the definition here, right? This box, guys, it really just says, you know, U is in tau prime if and only if the pre-image of U is in tau. That's just rephrasing it. It means exactly the same thing. So you can also just think of it in those terms. Okay, so U is in tau prime if and only if the pre-image belongs to tau. Now, what do you think I'm going to do next?
Similar to what we did in 2, or a double I.
Exactly. The same thing we did in the previous part. So what would I want to do here next?
Show that the pre-image preserves unions.
Okay, so I want to take the union of all of these, right? So since tau is a topology, it already preserves arbitrary unions. So the union of each one of these pre-images of U sub I didn't really talk about an index set here, but I should just put that there. This pre-image, or this union of these pre-images, is an element of tau as well. Okay, so you take a union of a bunch of things from tau, you get something else that's in tau. And now what can I do?
Take the re-image outside of the union, right?
So that's exactly right. Oops. One thing to remember, guys, pre-images respect both unions and intersections. If you take if you take images under a function, they will preserve unions, but not always intersections, unless the function is one-to-one. So this is kind of a good, that's way back to chapter 1, right, when we did kind of the review chapter. It's worth kind of getting that clear in your mind. Pre-images, just remember, pre-images are wonderful. They protect everything. Unions, intersections, any other set operations is going to be fine. So this is the same thing as the union of the pre-image of U sub I, and so therefore it is in tau, and so that means that the union of the U sub i's is in tau prime.